Let's take a look at a cheap solar charge controller from AliExpress, also available on eBay. Super ridiculously cheap for what's actually inside it. What's the catch here? But anyway, before we continue and before I disassemble it, let's take a good close look at this and how it gets used. So this unit, in its default status, shows the current battery voltage, and the little arrow there pointing to a light bulb shows that it's powering the load. It's got 3 sets of terminals here. It's got a set for the solar panel, it's got a set for the battery, and a set for the load. And it's important to note that when you're wiring this up, you should connect the battery first before the solar panel. I think that's because the open circuit of the solar panel could cause issues, but they do say that it can potentially damage it. That's also probably because the battery itself is powering the unit, but the standby current is only 2 milliamps, which is acceptable in the scale of this unit. It also has the USB outputs. Not testing them at full current. It does make quite bold statements, but I can test that later on. So to program this, it's suitable for use with, apparently, 12 or 24 volt batteries, and it's suitable for the technologies sealed lead acid, lithium, or lithium iron phosphate. So to go through the settings here, if you press the menu button once, it shows the current float voltage. There is a little image of a solar panel appears here when it's charging, little arrow, point to the battery, and you can change that if you wish. Any of these settings can be changed, say for instance, the float voltage by pressing and holding the menu button at that point in time, and then you can adjust it down or up, and then press and hold again to go back to the main setting. I think it also reverts back after a time. So the first setting is the float voltage. The second voltage is the minimum voltage that it will put power out to load. See the little arrow going to the light bulb there? The next setting, and because I'm explaining this, it reverts back to the start, but the next setting after that is the cutoff voltage. See the empty battery and the arrow to the load? If it goes below that voltage, it cuts off. It's worth mentioning that the minimum voltage for actually initiating power to the load, this one here, is the point at which it will cut back in. It's got a good sort of level. You can program it, the hysteresis, that it's not going to cycle on and off just based on the voltage fluctuating in the battery. The next mode is the timer mode. You can choose that when it gets, if you have 24 hour, that means it's going to be on all the time. But you can set it down to say at dusk you want it to come on and run for 8 hours. Or you can put it right down to 0, and if you do that, it will go in dusk to dawn. It will turn on at dusk and turn off at dawn again. The next mode is the battery type. B1 is the sealed lead acid batteries. B2 is the standard lithium-ion batteries, the one to charge up to for about 4.2 volts, and the next one is the lower voltage lithium iron phosphate type batteries, which I've just missed that because it reverted back. Oh, go back round again. B2, press and hold, and you can then go up to the lithium iron phosphate, or indeed just step back down to the sealed lead acid. I would recommend, just because this is using a computer to control the charging, I would recommend that you also have overcharge and over discharge protection on the battery itself, except for sealed lead acid, which is more resilient to a little bit of overcharging and stuff like that. Not that resilient though. Other things worth mentioning, I believe you can toggle the load on and off with this button. And in any mode other than the default setting, if I press this one and go into another mode, if you press the up button for a while, is this going to do it? I've not tried this. It reverts back to its default settings, its factory settings. Okay, now you've seen that, let's take it apart. I would also recommend that the battery that's connected to it does have a fuse in line. That does kind of make sense. Gets rid of the blue tack I was using to set that up at an angle because the display is not that clear. You may need to shine a flashlight on it. It doesn't light up, to the best of my knowledge. In fact, it definitely doesn't because I've seen the display inside. Rightio, let's disconnect this and open it up. It does have rising clamp terminals. This is good, but it's worth mentioning, and it's quite important that if you aren't careful putting wires into these, it's the rising clamp terminals that also have the little void below them. So you can stick a wire in and it feels as though it's going in, and you can tighten it up and then it will just pop right back out again because it can go underneath the terminal. It's worth mentioning that. The same applies to circuit breakers, some designs of circuit breaker, which isn't great because people can slot them over bus bars, tighten them up and think they've got a good connection, and then the wire just pops out or it starts burning. Okay, let's pop the back off this. I have shown this in another video when I was just looking at stuff that had arrived in the post. The back plate is metal. The reason it's metal is because it also acts as a kind of heatsink. Now these are available in different current ratings. This one is a 10 amp one, which means it can provide 10 amp to the load. But as with all these things, I do tend to recommend underrunning them because it's just better. They tend to be quite optimistic with their values. So the back comes off, revealing a not guaranteed connection onto the back of the transistors. So that also is a reason not to get too much current from a unit like this, because it will potentially overheat the transistors, and then they'll do weird things like failing and jamming on or doing nasty things. Now, rather annoyingly, it's a fairly complex circuit board, but really annoyingly, the LCD display is soldered on and there's circuitry underneath it, which to reverse engineer this, I'm going to have to remove that display. And while I could try desoldering it, the risk of damaging things while I do that is quite high. And since I got this to make a video about, what I'm probably going to do is just cut these leads here, the connections, and then that will let us get a closer look at this. But while we're here though, let's get these pads off the back of this. You could put your own pads on if you want. Let's see what these are. Are these all going to be MOSFETs, and are they all going to be the same type? Are they really? Just at first glance, there's no markings in those. There must be markings on. I shall have a closer look, but I can't see any markings in those at all. Wow, that's a good start. Okie dokie. Right. So I shall take some pictures and reverse engineer this now. One moment, please. Reverse engineering is complete, and let's explore. I have to say that took 3 nights of coming back and forward between the bench and then just getting exasperated and walking away. This was very hard to reverse engineer. This has a lot of circuitry in it, but it has all been reverse engineered and we can now explore it. Things worth noting. The most complex bit was the arrangement of the MOSFETs, because they're in tandem in series for the charge circuitry. The MOSFETs, which didn't have a visible number on them, and on closer inspection it turns out that someone's buffed all the numbers off. I took all the MOSFETs out after numbering them, put them in a component tester. They're all just standard N-channel MOSFETs with standard gate voltage, so nothing special there. So let's take a look at the circuitry. It's divided into blocks. So to power the circuitry, we've got a 5-volt supply over here. And the 5-volt supply provides an output on this USB port, and it's not a very high output. Why did they even include 2 USB ports? My advice, if you have one of these, is get hot melt glue and seal those up so nobody plugs anything in, because it can only deliver 500 milliamps, and it just so happens to use the same 5-volt supply as the microcontroller. And if you overload it by plugging in a phone or anything like that, it will make everything just shut down. Fortunately, it shuts down in a controlled manner, and by controlled manner I mean by losing control and all the MOSFETs turn on by default. So the load will be on and the solar panel will just be in charge mode continuously, from what I can see. Next module here is an overcurrent sense circuit. It's based on an LM358 op-amp, and if we take a look at the back of this circuit board, you'll see these big chunky, well, I can show you a version of this. You can see it's got big chunky bus bars going along here. It's interesting to note that the common bus bar is positive and everything is being sort of switched on the negative side. But you'll see that the plated through holes stop in this area, and then it's just a solid track going under there. That track is this bit of track here, and it's actually used for current sensing as well. you'll see a little tiny track coming off this pad. It's literally measuring the difference between the common 0 volt rail and the voltage drop across that pad, and it's 37 millivolts is the threshold level. It will do things like it will turn the MOSFET off directly, but it will also signal back to the microcontroller. The microcontroller has 20 pins. I was wondering if they'd done clever multiplexing to fit everything in, but they have, but they've not. The LCD display is driven directly from the microcontroller, which is a BL51F003B5. That is a generic 8051 architecture microcontroller with all the display drivers and analog to digital converters. It's a very competent little chip, but mass produced because it's out of the sort of like the proprietary architecture patent period or whatever it is. You find this in a lot of this base 8051 in a lot of Chinese stuff. I had to cut the LCD display off, but that's okay. It could be soldered back on, but having said that, it might just be if I wanted one of these, which I don't, it'd be cheaper just to buy another one. There's two of these ports here, one maybe for programming. I wonder if I don't know why there's two separate ones, but it's possible it is designed for a remote display. Not sure. The buttons are multiplexed onto a single analog input. And then there are two sections of circuitry over here that generate a MOSFET switching voltage reference to the 0 volt rail and also one reference to the solar panel's 0 volt rail. And after that, it's just loads of little voltage dividers and stuff like that and then it's all done in software. So let's take a look at the schematic, and I'll warn you in advance, the schematic, the first page of it is absolutely atrocious because I had to do it in spidery small text just to fit everything in. And I'll zoom up on this. Actually, I'll pause while I zoom up on this because I'll probably over zoom and resume. Okay. So this looks very densely packed and spidery simply because there's so much to actually cover in the driver of the MOSFETs. So here is a solar panel. The battery is effectively connected between the positive here and the negative here. The battery and the common to everything, and the 0 volt rail. And to be able to switch it completely, they have to have two sets of MOSFETs in series with the drains connected. It's very similar to the rechargeable lithium cells where you've got the little protector chip, where you've got the DW01 chip and a couple of MOSFETs back to back to do this. But the driving of these is much more complicated. So to drive these, they have to generate two supply rails. And they generate them from the main battery supply by going through a diode first, and then it goes to the 5-volt regulator. But then it has a bit of smoothing, and it's got a 2K2, 2200 ohm resistor, limiting the current to a Zener voltage level. It's a capacitor with a diode for polarity protection, which is odd. I guess this is all to protect against reverse connecting of stuff. And then they've got a 12 volt Zener, and that creates, see this pink dot, that creates the common gate control voltage for the MOSFETs that are referenced to the 0 volt rail, but also the one that switches the load here. But they also, to be able to switch this MOSFET, they have to create one that's referenced, because that's back to front, they have to create one that's referenced to the solar panel's negative. So this supply also goes via diode, limiting resistor, and then it's got another Zener balance supply, which goes to the solar negative, and that means that when the appropriate transistors are turned on, it will actually turn both these MOSFETs on. The MOSFETs are turned on in most unusual ways for some of them. Here is the base MOSFET in the charge circuit, and when the microcontroller powers it, very simple in this case, it turns on a transistor. Now, by default, the MOSFETs are all turned on with a resistor going up to their relevant plus volt supply, but they're turned off when the microcontroller actually sends a signal to these transistors. This is why if the microcontroller goes down because the 5 volts goes down, everything will just by default turn on because there's no control over these transistors anymore. The control over this MOSFET is heinous. It's very odd. So It is, where do I even start here? It's powered from, via this transistor from this rail, the rail that is referenced to the solar panels negative. If you're bored, I'm sorry, skip forward. The next pages of the schematic are so much easier. But it's really hard because the output from the microcontroller comes via a PNP transistor, which has its base just tied straight to the 0 volt rail. And the only way I can think that that's there is to detect if the batteries become disconnected or something. And it will then take the drive away from that. But then that would turn the output on. Maybe it's to detect that the battery's gone too low, the circuitry's shut down. It's very hard to say. But this transistor turns on this transistor, which then turns on this transistor, level shifters, and ultimately it ends up powering the MOSFET here. Yeah, looking at this, it's complex what they're doing here. There's the load control IGB MOSFET. And it is controlled from two sources. It's controlled from the microcontroller. By default, it will be on because of this pull-up resistor. But it can be turned off by the microcontroller, but it can also be turned off by the overload circuitry. I think I've covered everything. I knew this was going to be a nightmare. It was a nightmare to draw. It's been the hardest bit of the circuit. Hold on, I'll just leave it here a moment. If you want to just take a freeze frame and take a look at the circuitry. I've left a resistor value off up there, but I'm not too bothered about that. It's probably 100k. I could look for that right now, but hold on, I will. Hold on, let's find it. It's the one for this MOSFET. So it's O1D, which is 100k. I shall add that on. Where's the small pen? 100k. Most of the MOSFETs switching the resistor switching the MOSFETs are 100k. Right, let's go on to easier circuitry now. The next page is the voltage dividers. Let me show you their position on the actual circuit board. See these clusters of resistors here? These are the voltage dividers. So the first one is for the button. And normally the microcontroller input and the buttons will be floating around about 5 volts. If you press the left-hand button, it shunts it straight to 0 volts and it goes from 5 volts to 0 volts and it knows that button's been pressed. If you press this button instead, it puts two 18k resistors in series across from the 5 volts to 0 volts and you get 2.5 volts. Press this one and it puts two resistors in here versus that one there and you get 3.3 volts. So whichever switch is pressed, it will see the voltage go to that level. For the battery sensing, here is the battery supply rail, and it goes via 100k resistor and 18k resistor for the divider, little filtering capacitor, and then to the microcontroller so it can see the voltage of the battery. And it is rated theoretically 12 to 24 volts. I honestly wouldn't use this anywhere near 24 volts. I'd stick to just 12 volts, this system. It's pushing, like the regulator for the 5 volt supply is being pushed right up to its limit if you do use 24 volt batteries, because fully charged they'll be higher than 24 volts. Here is the, this bit is the, let me think, what is this? Ah, yes, dusk sensor, and this is heat. Okay, should have written them in before, not to worry. The dusk sensor has a pull-up resistor going to the 12 or 24 volt rail, and that forms part potential divider. But it is pulled negative by the solar panels negative, so that during the day when it's actually, if able to actually generate voltage, this will be pulled to quite a low voltage. However, at night time, when it's dark and the solar panel isn't producing any significant current, it can detect that on the voltage divider input and it knows that it's dusk. The next thing is the unexpected, hold on, in comes this. That there, in the vicinity of these MOSFETs, is a thermistor. It's a 10K NDC thermistor for temperature sensing. And it simply forms, as commonly across the 5 volt rail, 10k fixed resistor, 10k NDC thermistor, and the microcontroller can read it. But also notice that this transistor here from the overload circuitry can shunt that to the 0 volt rail via a 10 ohm resistor, and that's its way of signaling to the processor that there's a situation, that there's been an overload situation by emulating the thermistor actually getting hot. Much like many power tools do, they often have that 10k thermistor line. They'll shunt it to the 0 volt rail just to signal to tools to turn off because the battery is maybe running flat. Okay, next page is the buck regulator that can supply the miserable 500 milliamps at 5 volts. It's based on a standard chip. Let me just bring this in. It's an MC34063A. There are so many better options these days. That smacks of this being an old design that has been copied by everybody, and it's just they've never evolved it. But that's the chip there. The incoming supply goes via the diode and capacitor that's also then used to supply the MOSFET control voltages. But it comes to this chip. There's a current sense resistor, there's an inductor, Schottky diode, and it allows pulses of current. It pulses the output high, current flows through the inductor and charges up this capacitor. And it only does it in brief pulses though. And when it turns it off, the field collapses and also goes via this freewheel diode and also charged capacitor. So it's doing sort of double duty. But the inductor is the main thing. It's limiting current as it charges that. Once the voltage reaches 5 volts, this potential divider based on a 15k resistor and two 10k resistors in parallel, just their standard value here, they did that so they could tune it. That reaches the 1.25 volt threshold, and that's what controls the voltage and output. That goes straight to the USB connectors, but then also via a 4.7 ohm resistor to the microcontroller supply. Now we're past that first page, it's all getting much more straightforward. Here is the overcurrent sense circuitry that literally measures the voltage across that little tiny bit of track. So they set using multiple resistors in series for precision. They set a voltage on the input of this op-amp. An op-amp compares two voltages, and if they cross in a particular direction, it will change the state of the output. And you can choose which polarity it's going to be that and when they reach that threshold, it will just change the output's polarity. So they've got the input set at 37 millivolts, and the current sense is literally between that end of that track and the 0 volt rail that this is referencing to. So it can see if the voltage across that, if there's a short circuit in the output and it rises up to 37 millivolts or higher. And when it does, the output potentially goes high. That then provides positive feedback to that to actually give a more decisive operation. But it also drives this transistor, which is the one that pulls the NTC down to tell the microcontroller that something's gone wrong. But it also directly controls the MOSFET. Now the MOSFET is normally pulled to an on state by this resistor, and this transistor is used to turn it off. It can be turned off by the microcontroller, or it can be turned off by this overload situation where it will just basically take control and it will just override that because that's the fastest way it can do it. That then only becomes dependent on the value of these capacitors for the time it's going to take to do that. And that is it. I wish it was that easy to actually reverse engineer. But there we have it. Interesting design. There are other positions on the back for adding more MOSFETs if you wanted. I guess other models have those MOSFETs. But it does work. I mean, I wouldn't trust it to have it be anything critical, and it says it's rated for, say, 10 amps. Would you really use it at 10 amps? I'm not so sure. I wouldn't put a really huge solar panel on because there is the risk of if it puts out too much current, it's actually going to overwhelm the circuitry or cause the MOSFETs to get too hot, although theoretically thermal protection would protect against that. And the output is just a single MOSFET to that to the load with that fault sensing. But as always with the battery, add your own fuse protection to the battery. It's a wise thing to do. It's interesting. I mean, the driving of the MOSFETs was the most interesting bit in this reverse engineer, and it took the longest because it's so weird, particularly that transistor, that PNP transistor that switches the signal output from the microcontroller just by being turned on by that resistor. That took me a bit of puzzling to work out. But there we have it, the charge controller. Okay for hobby projects, but I wouldn't recommend it for any sort of major professional applications.